All right, so let's proceed with the ideas that we had in the previous class about unitary triangulation. All right, some applications of that. So let me do one after the other. So some applications. Applications of Schur's theorem. 1. So what we have seen was that if all our matrices are n cross n complex matrices, fine. So the theorem says that, look at this sigma A. So A is U star, or I think we wrote that there exists an unitary matrix U such that U star AU is T, an upper triangular matrix. Fine, an upper triangular matrix. Also, eigenvalues of A was same as diagonal entries of T. Fine. So sigma A is same as T11, T22, Tnn. So sigma A is just this, where T is Tij. All right. Fine, n cross n. So from here we can easily conclude that this will imply that if I look at trace of A is same as trace of U star AU, or trace of A times U star, because U star is identity, which is same as trace of U star AU, which is same as trace of T, which is same as T11 till Tnn, all right, which is same as summation over lambda belonging to sigma A, or sum of eigenvalues of A. So when we trying to prove it the first time, there was a quite complication involved, but using the Schur's lemma everything is nice. What about determinant of A? Determinant of A is same as determinant of U star AU, by the same argument that we did here, the determinant of A is same as determinant of A into I, and then we can multiply them out. So which is same as determinant of T, which is same as T11 into T22 into Tnn, which is nothing but product of eigenvalues. So you could do them directly, so simply. All right, there is nothing much that needs to be done here. Fine. So this is important that I would like you to understand. The second thing I would like to say here is definition. So there is a difference between what is called unitarily similarity and similarity. For similarity, what we wanted was similarity. We needed an invertible matrix P or invertible matrix S such that A is equal to SB S inverse. All right. So they say that A and B are similar. This is what we said. All right. At no place we said that we need unitary. We just needed similarity, means invertible matrix S. S invertible. That's all we needed. Fine. Now we are saying that unitarily similar. So when you say unitarily similar, we need S to be a unitary matrix. So we are putting an astringent condition that in place of S being just non-singular, we want S to be unitary itself. All right. And why do we want it? Because unitary always helps us in trying to understand something more, that if I have a unitary transformation S, so if U is unitary, then the length of any vector x remains the same, this for all x. All right. fine. That is not true when I look at the similarity here with respect to invertibility. So, in some sense unitary similarity is more stringent, and we follow mostly in our calculations because the norm of the vector does not change, fine. It may happen that some of the entries after calculation may become very small, but it may get taken care of by something which are larger and so on, but everything cannot become a smaller, and some things are basically there are some things which are positive about it, that the size does not change in some sense, all right, fine. So, as a example, let us look at this example to differentiate between the two example. Let us look at this matrix A, which is 3 2 minus 1 0 and B as 1 1 0 2, fine. So, I would like you to see that the eigenvalues of these two, so eigenvalues of this is already B is upper triangular, and therefore, sigma of B consists of just 1 2 and B is diagonalizable. Why it is diagonalizable? B is diagonalizable because it has distinct eigenvalues. Fine. So, I can look at it. What about A? What are the eigenvalues of A? So, let us compute the eigenvalues of A. So, x minus 3 minus 2 1 x, determinant of this is x square minus 3x plus 2, which is same as x minus 1 into x minus 2. So, this is also 1 2. So, A is also diagonalizable, A is also diagonalizable. So, what we have is, for A I will get a matrix A P1 such that P1 star P1 inverse A P1 will be equal to 1 0 0 2. For B I will get P2 inverse B P2 will also be equal to 1 0 0 2, and therefore, I can say that this implies that P1 inverse A P1 is equal to P2 inverse B P2, and that will imply that A is equal to P1 P2 inverse B times P2 P1 inverse, which is same as P2 P1 inverse whole inverse B times P2 P1 inverse, all right. So, A and B are similar, A and B are similar, all right. Can we say that they are unitarily similar or not? So, our question, are A and B unitarily similar, all right. So, I would like you to see that they are not unitarily similar because their sizes are different. Look at the size of A. The size of A, if I look at, in some sense, I am not giving you what the idea of size is, but I want to look at the size of A in some sense, which is nothing but, if you remember, our in matrices, n cross n matrices, we looked at the trace, all right, the inner product was, inner product between A and B was B transpose A, compute that and look at the trace of that, which also corresponded to looking at dot product of each entry itself. So, here it will be nothing but a square root of 3 square plus 2 square plus minus 1 square, which is same as the square root of 9 plus 4 plus 1, which is the square root of 14. But what about norm of B? Norm of B is nothing but a square root of 1 square plus 1 square plus 2 square, which is the square root of 6, all right. So, they are not equal. Norm of A is not equal to norm of B, all right. This will imply that A and B are not unitarily similar. Fine. So, again understand it, if they were unitarily similar, that will imply that unitarily similar will imply that the length of A and the length of B have to be the same, fine. Here length of A is not the same as the length of B, therefore, there is a contradiction, fine. But they are similar as such, this is what we saw, that they are similar, fine. So, similarity may not imply unitarily similar, but unitarily similarity will imply similarity, all right. So, you need to keep track of that. This is very important idea. So, I would like you to look at some examples where you can prove that two matrices are unitarily similar by some unitary matrix and so on. Fine. Now, let us look at the next idea, where we look at now diagonalizity of special matrices. So, definition of what is called a similar matrix definition. A is n cross n, then A is said to be a normal matrix if A times A star is equal to A star A. All right. So, A is a square matrix and we are putting this stringent condition that A times A star is equal to A star A. Fine. Example. So, look at any, so let A be a symmetric matrix. What does symmetric matrix mean? This means that A transpose is equal to A, and symmetric means I am looking at real entries, A with real entries, and therefore A times A star will be equal to A times A transpose, which is A square itself, which will be equal to A transpose, which is A star A. Fine. If I have A with complex entries, fine, then I need A star to be equal to A, that is A is Hermitian. Fine. If A is Hermitian, this will imply that A times A star will be equal to A times A, which is same as A star A. Fine. So, every Hermitian matrix is normal. What about skew Hermitian? A skew Hermitian. So, skew Hermitian means A star is equal to minus A. So, if I want to compute A times A star, it will be equal to A times minus A, which will be same as minus A times A, which will be same as A star A. So, again this is also true for me, all right. So, whether I am looking at Hermitian matrix or skew Hermitian matrix, they are normal matrices itself. You also have unitary matrices which also satisfy this, because for unitary matrix 3, U unitary implies U times U star is equal to U star U is equal to identity, all right. So, unitary matrices are also normal matrices and so on. So, there are lots of examples of normal matrices. So, we want to prove that every normal matrix can be diagonalized, all right. So, let us try to prove that part. So, theorem, let A be an n cross n normal matrix, then there exists a unitary matrix U such that U star AU is a diagonal matrix, all right. Or same thing as saying that AU is equal to, if I write this as D, it is UD, or which is same thing as writing as A is equal to UD U star. Fine. This is important that you can write it in whatever way you like, it depends on you, and accordingly proceed with all the mathematics that you want to do. Fine. So, let us prove this. This is a very simple proof with what we have learned till now. So, what we know is by Schur's lemma, by Schur's theorem implies there exists a unitary matrix U such that U star AU is T, an upper triangular matrix. Fine. So, you have U star AU as an upper triangular matrix. Let us try to understand what do I mean by now using normality. At this stage when I am writing this, I have not used the idea of normal. Now let us use the idea of normal. So what does normality mean? So normal implies A times A star should be equal to A star A. Fine? Is that okay? So this will also imply, and is implied by, because U is a unitary matrix, I can just multiply by U on both the sides, or I can write A in terms of whatever it is. So if I write A here, I already wrote, if I look at this part here, you can write like this. So I can write A as U d U star I am writing. So here it will become, so let's write A here. So here A is equal to U t U star. All right, fine. Just multiplying by U and U star on both the sides. So this is equivalent to saying that U t U star whole star is same as U t U star whole star into U t U star. Fine. Which is same thing as looking at, just multiply it out, you get U t U star. What about this? This is nothing but U t star U star. Right? Fine. What about this part? This is U star star, again U here, t star here, and U star will come here, U t U star. So this was just looking at the star, taking a star both the sides. Now I can look at associativity of the matrix product. These two matrices are identity. So I get U t star U star is equal to, again here t U star U is identity. So I get U t star t U star. Fine. So now I can look at the U is an invertible matrix, U is unitary, so invertible, and therefore I can multiply by U star on the left and U on the right, and therefore this will imply that this is same as T t star is equal to T star T. Fine. U is unitary, implies invertible, or whatever it is you want to say, or just multiply by U star on left and U on right. So whatever way you want to understand it. So normality implies that, normal tells me this part, but this part is equivalent to saying that the triangular matrix that I got should also be normal. So A is normal implies the corresponding T, corresponding upper triangular matrix must also be normal. All right. And now let us remember one result where we said that if I have an upper triangular matrix, so the T t star is T star T, then T has to be a diagonal matrix. We had done it for the lower triangular also. So let's try to understand this again. So I have T here, which is upper triangular. So T11, T12, T1n. Now I am looking at, so this is T. I want to look at T star. T star we are saying this is equal to, fine. So T star is T11 bar, T12 bar. There is a 0 here. Fine. So there will be 0 here, and T1n bar. This is what T star will be. We are saying that this is equal to T here and T star here. So what is T? T11, T12, T1n, 0 here, something here. T star writes T11 bar, T12 bar, T1n bar, something here and 0 here. Fine. So just multiply it out. Look at the 1 1 entry. 1 1 entry of the product. All right. If you look at the 1 1 entry of the product, this entry, the left hand side LHS is equal to mod of T11 square. What about the right hand side? The right hand side is T11 this square plus T12 this square plus T1n this square. All right. So absolute value of so many things. So what we are saying is that this should be equal to this. These are complex numbers, and we are looking at the absolute value square of this. So these are positive numbers or non-negative numbers, positive, or positive or 0, all of them. So when I am saying that this is equal to this, it means that, so this implies mod of T12 square plus mod of T13 square plus mod of T1n square is 0, implies each of these, each of T12, T13 till T1n must be the 0 complex number. Fine. Now once you have done that, then we can look at the 2-2 entry. After this, we can look at the 2-2 entry. We can look at the 2-2 entry, and from there conclude that the 2-2 entry must be 0. So this 2-2 till 2-2n, so they will also become 0. So at the first stage we have shown that this is 0. So that implies that this part is 0. All right. At the next stage T23, so this will imply that T23 will be equal to 0 equal to T24 is equal to T2n. All right, fine. So what we will see here is that, so what we see, this part implies that the matrix T basically looks as T11, T22, Tnn. All right. The rest of the entries are 0. Fine. So we have shown here that because of normality, A is normal implies Tt star is T star T, and T is upper triangular implies T is diagonal. This was there in one of the exercise also in, I think, first or second slide, or after matrix multiplication, I think. Fine. So you have to keep track of things. So therefore we have proved that if A is a normal matrix, which implies that A star is A star A, which implies T star T is equal to T star, and hence U star AU is a diagonal matrix. Fine. So for any normal matrix, diagonalization is true, and you have to keep track of that this is one of the most important results that we have here. We will look at its applications now. So let us try to have an application of this. Applications. One, every Hermitian matrix oblique skew Hermitian matrix or unitary matrix, so on, are diagonalizable. All right. This is very important that all of them, they can be diagonalized. Fine. And what do I mean by say diagonalized means? So we can find n linearly independent eigenvectors for them. Is that okay? Fine. And you saw that you can do it using unitary matrices. First part, second. All right. They are diagonalizable using unitary matrix. What does it mean? Recall, this matrix will also give you eigenvectors. All right, they gave eigenvectors, because when I am looking at U star AU is diagonal, this is same thing as saying that AU is equal to UD, and therefore A of U1, U2 till UN is equal to U1 to UN times diagonal D1 to DN, implies A of UI is equal to DI/UI. All right, fine. So when you are saying that they are using unitary matrix, it means that the rows of A of U or the columns of U both are orthonormal matrices. So we are saying that in this case, the columns of U are orthonormal basis of Cn over C, fine, or which is same thing as saying that the columns of U are nothing but the eigenvectors. Columns of U are eigenvectors of A, fine. So we are saying that this, so what we are saying is, so that is the eigenvectors of A form an orthonormal basis of Cn over C. Is that okay? So they form an orthonormal basis. That's very, very important, that whatever we are doing, we are able to get an orthonormal basis of Cn over C, and that is true for Hermitian matrix, skew Hermitian matrix, or for that matter any normal matrix. All right. In the next class we will try to understand them in a different language. Fine. So I want you to keep track of things here, what I mean by saying things. So as the last part, let me rewrite this part in a different language now. So let's try to understand what we are saying. So third part. So what I am saying is that I have a matrix U, which is U1, U2, Un. Let us multiply it and see what happens. So I want to multiply U and U star. I know that this is supposed to be identity because U is a unitary matrix. So this is same as U1, U2, Un times the transpose of it. So U1 star, U2 star, Un star. So I am writing identity as, just multiply it, you get U1, U1 star plus so on till Un star. Fine. I am writing like this. So we are able to decompose, In as sum of matrices of the form Ui star. Fine. Let me write this as Pi. Fine. Then what we see is that identity is P1 plus P2 plus Pn. What is Pi square? Pi square is Ui star into Ui star. This part Ui star, Ui is nothing but the dot product or the standard dot product of complex numbers. So I get this as Ui star itself, which is Pi, and Pi star is same as Pi. So we have written I as, so these Pi's are orthogonal projections. Fine. So we have written I as sum of orthogonal projections. Fine. Each of them will have rank 1. So each Pi will have rank 1. If I just want to look at, say, P1 plus P2 plus P3, this is also an orthogonal projector, orthogonal projection on the subspace linear span of U1, U2, U3. Fine. Their rank will be 3 because they are orthogonal and they are linearly independent and so on. Fine. So I have got In like this. If I look at A is nothing but A times In, which is same as A of U1, U1 star plus U2, U2 star plus Un star. I should have written a star here because this is what we are looking at. So this is equal to A times U1 is lambda U1. What is A U1? It is an eigenvalue. So I wrote it as D1, D2, I think. So A U1 is D times U1 star. I think, just a minute, I should not get confused. So let me write this itself, U1, U2, U3 projection. All right. So D of this plus, not D1 it was, yeah, D2 U2 U2 star plus Dn Un star. So what we are saying here is that I have these spaces U1, U2, Un. I have these vectors. The action of A, if I look at what it does, it expands or it elongates or whatever you want to say, it changes by multiplying by Di. All right. the action of A on ui is by multiplying by the scalar di. Is that okay? So, this is what you have to be careful about, that A is a matrix which may look quite different, but if I look at the action of A on each of these subspaces, if I look at the action of A on the subspace U1 or linear span of U1, if you want to say, if you want to be completely correct, similarly linear span of U2, then it is just by multiplying by a scalar quantity and nothing else. In place of multiplying by some vector, we are multiplying by a scalar quantity. Is that okay? So, you have to keep track of this. We will look at this again when we come to Hermitian matrix. We will add something extra to these ideas. All right. So, that is all for now. Thank you.